Now, coming to the next part of this integration, as we have seen that, well, that this integration, where's the, sorry, where's the initial part? So, yeah, so this integration, we have evaluated this part, right? Which comes out to be 0. This part comes out to be Dirac delta, isn't it? Now we'll come to the third part, which has integration 0 to 2 pi sine nx cos mx dx. Alright, so integration 0 to 2 pi sine nx cos mx will give us what we'll see here. So this will give us, actually this is not the line, we have more things to do here. So that part, what does it contain? It contains bn, right? Bn and then this part. So let us write that down. Bn integration 0 to 2 pi sine nx cos mx dx will give us, we cannot evaluate this right now, in the sense we cannot evaluate this directly. So what we do is we this again break this into an identity. An identity, we have already said that it simplifies things down, right? So what will the identity do? Identity breaks this into two parts, 0 to 2 pi sine n plus m x dx plus half, there's a half here, okay, yeah. Okay, let us move this bracket because this bracket is making things complicated. Half integration 0 to 2 pi sine n minus m x dx. All right, so now we know that integration over 0 to 2 pi sine kx is gives us 0. So considering k is equals to m plus n and considering k prime is equals to m minus n, we can easily say that both this half, that is this half sine m plus n dx and this half sine m minus n dx will give us 0, because they both are integration over 2 pi and both have sine kx in it. So sine kx integrated over 0 to 2 pi, like integrated over 2 pi, gives us 0. So both this term individually gives us 0. So this third term will also give us 0, right? So what we can say, now this is the end of it. Alright, now we'll go back to the original equation, this one. So this, what does this say? So again we'll write it once again and then we'll simplify it. So coming back to the violet color, what we can say is integration 0 to 2 pi f of x cos mx dx is equals to a0 by 2 integration 0 to 2 pi cos mx dx plus summation n is equals to 1, that is summation over n integration 0 to 2 pi cos nx cos mx dx plus bn integration 0 to 2 pi sin nx cos mx dx gives us what? Gives us integration 0 to 2 pi, writing the left hand side first, f of x cos mx dx is equals to 0. The first term was 0 plus the Dirac delta term and again a 0 term plus summation n is equals to 1, that is summation over n pi delta mn again plus 0. So what is it? It is nothing but, and what does pi delta m give? Pi delta mn gives us pi when m is equals to n, else 0 when m is not equals to n, isn't it? So we can say for m is equals to n, what we can say? We can say that 0 to 2 pi f of x cos mx dx is equals to an pi, where we have put m is equal to n. Alright, now also since m is equals to n, we can also write that 0 to 2 pi f of x cos nx dx is equals to an pi, m and n being equal, so we can replace m with n and n with m. So what does this give? This gives us that an is equals to 1 by pi integration 0 to 2 pi f of x cos nx dx, right? So this is what our an is. And similarly, I'm not doing the calculation because the calculation is exactly same as this, as the calculation of an. We can say that bn comes out to be 1 by pi integration 0 to 2 pi f of x sin nx dx. Just remember that an has the term cos nx and bn has the term sin nx. Rest all look similar. Look, both have 1 by pi in it, both have integration 0 to 2 pi in it, both have f of x as the first term of inside the integration, and dx in the end. That is necessary, that is like you cannot avoid it. Just the term being different is an has cos nx, bn has sin nx. That's the only difference in an and bn's expression, and an and bn being the what? The coefficient of Fourier series. We had found out a naught, now we have found out an and bn. So we can say that, sorry, this is an, this is bn, and where had we found a naught? Wait, and this is a naught. All right, in order to find Fourier series, I believe that you should learn this expression instead of deriving it, because in exam we won't have, like, you people won't have that much of time to derive the expression for a naught, an and bn, and then find the coefficients separately. So I would say you should prefer learning the expression by heart and then just put the value and find the result. So you will be given f of x, you will be given the integral, like the interval over which to integrate, and what you just need to do is just put sin nx, cos nx term, and put f of x and multiply and integrate. And also I would say that you better learn the integration formulas for different kind of integration, different special functions, different terms related to cos and sine, like integration cos square theta, integration cos 2 theta. These integrations should be by the tip of your pen, so you better learn this, because these will make things easier, nothing extra, like. So we have actually, what we have done here is we have actually learned how to bring out the expression for a naught, an, and bn, the three coefficients of Fourier series. All right, this was our target. Now let us discuss some of the cases. Like, what are the cases? Cases in the sense, what if we change the interval? Interval in the sense, what if we change the interval from, we have till now calculated for the interval 0 to 2 pi, right? So the overall interval is 2 pi, but the upper limit being 2 pi, lower limit being 0. What if we take a case, sorry, what if we take a case where the upper limit is minus pi, sorry, lower limit is minus pi, and the upper limit is pi, plus pi. Again, in the same way, the expression of a naught will just change by 1 by 2 pi. The limits will change, the limits of integration will only change, rest all will fall into the same place, like nothing will change as such. So a naught turns out to be 1 by pi integration minus pi to plus pi f of x dx. All right, now how will the expression for a n change? Nothing, just change the limits. So 1 by pi integration minus pi to plus pi f of x cos nx dx. Alright, how will bn change? Same way, 1 by pi minus pi to plus pi f of x sine nx dx. So look, there's nothing as such changing in these expressions. What is changing is the limit of integration, like the interval being 2 pi, because we know pi minus of minus pi is 2 pi, interval being constant, but the upper limit and the lower limit of the integration is just changing according to the new set of interval. So we will just change the limits of integration, and the rest of the things will remain the same. Alright, now what if we change the interval to 0 to 2l? Alright, so what if we change the interval to 0 to 2l? Let us change and see. This is another case, so let us change the color at least. Let us use green. Alright, now our interval is 0 to 2l. Look, we were talking about 0 to 2 pi, but then our interval have now changed to L. So there's a scale change here. So what do we need to do? Let us first write the expression, Fourier series expression. F of z changes to a naught by 2 plus summation n is equals to 1 n cos nz plus bn sin nz. Alright, where is the scale change happening? Here. What is the scale change happening? The scale change is where we have considered 2 pi x as 2lz, isn't it? Because 2 pi here has changed to to L. So Z changes to pi x by L. This is called the scale change factor. This is where the scale, our scale is changing. Alright. So what will our expression, transformed expression look like? It will look like f of x is equals to a naught by 2 plus summation n is equals to 1 an cos n pi x by L plus bn sine n pi x by L, and the bracket closes here. Alright. So earlier we did not have n pi x by L as the theta of cos and sine, but now we have because of the scale change factor, because we are changing the scale from 0 to 2 pi to 0 to 2L. So how will this affect our a naught, an and bn? So this will affect our a naught, an and bn in the following way. A naught will change into 1 by L, 1 by pi it was earlier. So 1 by pi will change to 1 by L, 0 to 2L, f of x dx. That's it. An will change into 1 by L, 0 to 2 pi, f of x cos n pi x by L dx. And how will bn change? bn will change by 1 by L, 0 to 2L, f of x sine n pi x by L into dx. So what we have done, we have just put the scale change factor, which is n pi x by L, and what we have changed what we have done is we have changed the pi into L, right? So similarly, what if our interval, again another case, so we'll prefer changing the color. Let us change this to pink. So again, when we have another case, when the interval changes from minus L to L, similarly all these terms will also change. Like a naught, what will a naught become? A naught will become 1 by L integration minus L to plus L f of x dx, right? How will the an change? So an will change like 1 by L integration minus L to plus L f of x cos n pi x by L dx, and bn will change as 1 by L minus L to plus L f of x sine n pi x by L dx. Alright, so these what we have discussed till now. Initially we had our interval from 0 to 2 pi, then we changed our interval from minus pi to plus pi, then we changed our interval from 0 to 2L, and at last we changed our interval from minus L to plus L. Alright, so these were our four intervals, and we had changed, and we had we had just derived our expression for 0 to plus 2 pi. We had just derived our expression for the first case, that is 0 to 2 pi, and after that we had just put the values of the rest of the interval limits into these expressions of a naught, an and bn, and then what we have done is we have put the value and found the result. So we have just derived the expression for a naught, an and bn for 0 to 2 pi case, and we have put the others, these like minus pi to plus pi, 0 to 2l, and minus l to plus l values into those expressions of 0 to 2 pi, and we have found the results. Like results in the sense how will the values of a naught, an, and vn change accordingly. So that's it for now. Let's end our lecture here.